Hi everyone, this video today is about single and double displacement reactions. It is from 5.2 in McGraw-Hill Ryerson on Science textbook, grade 10s. Take a minute and just look at the two pictures that we have down below. See if you can figure out, just based on those pictures, what is actually happening in a single and double displacement reaction. First thing I want to look at is a quick review of where we've covered so far. Remember, a synthesis reaction is when two things combine to form a larger compound, and a decomposition reaction is when two things break apart. And so we looked at the case of hydrogen and oxygen becoming water vapor, and we looked at the case of TNT with heat, with fire, exploding to become all those things listed there. Now you notice I haven't talked about this before, but there was a picture in the synthesis reaction of two dancers. And this is hopefully helpful in all these situations. You can consider the synthesis reaction of two dancers coming together to form a couple who is dancing together. Or you could consider it in the case of two people are dancing and one of them so bad, like maybe me, that that person decides, you know what, I'm better off to dance on my own. So maybe that is a helpful analogy for you. Moving on to single and double displacement reactions now for today. A single displacement reaction occurs when an element takes the place of another element in a compound. Metals will take the place of metals, and nonmetals will take the place of nonmetals. And so from this picture that we have in front of us, you can see that we have two people dancing together, and then this guy comes in and he takes the place of the other guy. And the other guy goes off happily dancing by himself. And so that is an example of a single displacement reaction. One person or one element takes the place of another within a compound. Well, what does an example actually look like? Well, here we go. We have aluminum plus copper chloride, and what happens is the copper has taken the place, or the aluminum has taken the place of the copper, and so you get aluminum chloride, and then we get copper by itself. Now, make sure that when you're doing this, that you're first starting by drawing the cross-down method to start, just so that we get the subscripts correct. We're going to have some practice with that at the end of the video, but that's how I get the subscripts. After you get the subscripts, the little numbers in the corner, then you go ahead and you balance the chemical equation by putting the coefficients in front. Here's an example where we replace a nonmetal with a nonmetal. So we have fluorine, which we know is a diatomic molecule, so it only exists as F2. It only exists two together as its element, naturally occurring in nature. And so it has replaced the iodine. And the iodine now becomes, again, that's a diatomic molecule, so it becomes I2. And then we have sodium fluoride that's left over. A double displacement reaction occurs when positive ions of two different compounds exchange places, resulting in two substances, one of which may be a precipitate. And so what we have here is two people dancing together, and what happens is literally you can see the two ladies swap places. And so maybe it's grandparents and their kids, who knows? But they've switched places. And so that's what's happening in a double displacement reaction. An example of a double displacement reaction is something like this. Quite a cool thing that forms, a precipitate, when we mix silver nitrate with potassium chromate. That gives us silver chromate, which is that reddish precipitate, and potassium nitrate. So the metals have switched places with what they're matched up with. Notice that chromate CrO4 and nitrate NO3 are both polyatomic ions. Chromate is not listed on our polyatomic ions on our Chemistry Best Friend Forever page. However, it is something that is also polyatomic. There are way more than we're going to go over explicitly in this course. Now it says identify the type of displacement that has happened. And what we can see is we've got four different situations. And this first case, we can see that we had sodium paired up with sulfur, hydrogen paired up with chlorine, and now we have sodium paired up with chlorine and hydrogen paired up with sulfur. They have switched. Literally, these two things have switched. And so this is a double displacement reaction. Double displacement reaction. In the second case, we have hydrochloric acid and zinc, and then we get zinc chloride plus hydrogen gas. And you'll notice there that the descriptions of what state it's in is also listed there. In much of the homework you're going to work on today, it is listed. Not always, but often it is. And so aqueous means it's dissolved in water, S means solid, G means a gas. And so you can see there that what's happened is the zinc has replaced the hydrogen. And so that is a single displacement reaction. In the third case, we have lithium plus chlorine gas, it's a diatomic molecule. And when we cross down the two, we end up getting just LiCl, lithium chloride. And so that is clearly going to be a synthesis reaction. They're synthesizing and becoming one. And then this last one, we have H2CO3, which if you remember from the last lesson, is carbonic acid. And it's going to break down to become water and carbon dioxide. Carbon dioxide. Shouldn't have a line there, but let's get rid of that. Well, that's all well and good. We know that, but didn't we see it the other way around yesterday? And in fact, we did. We saw that yesterday as a synthesis reaction, but here it's a decomposition reaction. What's so important about that? Well, carbonic acid is what makes up, or what causes the fizz in pop. So when you open a can of pop, carbonic acid begins to form into water and carbon dioxide, and that's what gives you the fizziness of the pop. In order to get the carbonic acid into the pop in the first place, you have to do this in reverse, which requires a little bit of using electricity to do that. And then you have this nice fizzy pop to be able to drink. Let's look at one more type of question that we're going to see in our homework today. Identify the type of displacement that you expect to happen and finish writing the chemical equation. Be sure to balance it as well. Well, we have silver nitrate. Remember, this is a polyatomic, so it goes all together. And we have aluminum. And so what we're expecting is we're expecting the metal to replace the other metal. And so what we should get, and I'm just going to write it up above here first, aluminum and nitrogen, or sorry, aluminum and nitrate, and then we should have silver by itself. Now, the reason I've written it up above is because I have to make sure that I use the appropriate charges and cross them down properly. So here we go. The first one is that aluminum, if you find that on your periodic table, aluminum has a charge of 3+, nitrate has a charge of 1-. When you cross those down, what you get is aluminum, nitrate, NO3, with a 3 outside brackets, because the 3 applies to both the number of nitrogen and the number of oxygen is tripled as well. So make sure you put brackets there. And then silver, we know, is not a diatomic molecule, so it's just going to exist by itself in nature. And so how do we go about balancing this? The first thing we do is we can list the reactants and the products. And we know that the reactants are silver nitrate, we're treating as a single thing, and then we have aluminum. And so initially we have 1 silver, 1 nitrate, and 1 aluminum. And on the product side, we have 1 silver, 3 nitrate, because the NO3, 3 outside the brackets, and 1 aluminum. So the first thing I need to do is I need to triple the nitrate. So I'm going to go ahead and I'm going to do something that's going to triple that nitrate. So I'm going to have to write a 3 over here on the reactant side. That's also going to triple the number of silver. Well, because silver is by itself on the product side, if I write a 3 there, now that is balanced. I have the same number of atoms on both the reactants and product side. Excellent, it's been balanced. The second equation is not KL, because L isn't, there's no small KL as an element. It's an I for iodine. And so we have potassium iodide, and we have lead nitrate. And so because of that, what we would expect to happen is we would actually expect these to switch. That is a double displacement reaction. We should have identified that up above as well. The first one was a single displacement. This one is a double displacement. And those are going to switch. So what I'm going to get, again, I'm going to write these up above. I'm going to write K. I'm going to look at the charges here in a minute. I'm going to get K and NO3. And then the other thing I'm going to have is going to be lead and iodine. Okay, well, potassium has a charge of 1 plus. Nitrate has a charge of 1 minus. And we can just read those off of the periodic table or the common polyatomic ions on our chemistry BFF page. And when I cross those down, I get just KNO3. Okay, well, that's great. Straightforward enough right now, hopefully. Now we have lead iodide. Well, if you look at lead, it's actually going to be this 82nd element on your periodic table. And you'll notice that it is actually one of those multivalent metals, or multivalent transition metals, rather. So it has a 2 plus or a 4 plus. Well, how do I know what one it is? Well, let's go back to this, and let's see if we can determine what lead was here, because let's do the reverse cross-down method. So I'm going to go and cross up, if you will. So I'm going to take the lead and the NO3 that had a charge of 2. I'm going to cross the 2 up here. I'm going to cross, we'll assume there's a 1 there up here. Well, that would give me Pb2 plus NO3 1 minus. We know that the NO3 has a charge of 1 minus, so that means I must have lead 2 iodide, not lead 4 iodide. So now I can go over to the other side in my product side and write a 2 plus. My iodine has a charge of 1 minus, so this becomes Pbi2. Now I need to balance it. I'm going to start with potassium. Nitrate is a polyatomic, so I'm going to keep that together. Lead and iodine. In my reactant side and my product side, let's see what we get. Initially, we have 1 potassium, we have 1 iodine, we have 1 lead, and we have 2 nitrate. On the product side, we initially have 1 potassium, we have 2 iodine, because it's I2, we have 1 lead, and we have 1 nitrate. So it almost seems like it's there, and probably because we're so close, it should just be factors of 2 here that do it. Let's start by first doubling the iodine. So I'm going to double the iodine. So I'm going to get 2 there. I'm going to write a 2 out in front of the K and the I on the left on the reactant side. That's also going to double the number of potassium. Okay, we'll come back to that in a minute. So if I've doubled the number of potassium and I also need to double the number of nitrate on the product side, if I add the 2 in front of the KNO3, then that doubles the potassium, doubles the nitrate. It is now balanced. And we've now identified the type of displacement. We've finished writing the chemical equation by balancing it as well, and we have finished answering the question. Hope that's helpful. If you have any questions, feel free to contact me.